Hi, I'm David Hetherington. I'm a model-based systems engineering consultant. I work with a variety of clients on a range of systems. However, my specialties are functional safety and failure analysis. I volunteer with the International Council on Systems Engineering. Within INCOSE, we have a working group for automotive, and I'm leading a little project called Models in the Supply Chain. We're exploring the complexities of passing models between companies. This spring, we have some space for a few students to work with us to explore the practical techniques and challenges of passing these sorts of systems engineering models around the supply chain, and in doing so, do a capstone project for their university.
From an automotive point of view, we work on systems. Systems are composed of multiple components. The case we are interested in is the case in which the components are provided by different suppliers. In such a system, it can be very difficult to predict how the system will behave. We attack this problem by modeling each component as having a state machine, and the state machines go through different transitions, and as they do transition from state to state, they send each other events, and the events then cause the other state machines to transition as well. And here you see this would be a typical startup sequence with the auto now being up and running. Now, some of you may never have seen state machines, so next Lamont McAlilly is going to demonstrate a very simple state machine of a traffic light with red, yellow, and green states using the tool Cameo Systems Modeler. Next, Eric Cortez is going to demonstrate a somewhat more complicated state machine in simulating using the tool Sparks Enterprise Architect. Finally, I'm going to introduce a more specific automotive case of a power management chip and a microprocessor booting using Cameo Systems Modeler and IBM Rhapsody.
Hello, my name is Lamont McAlilly, and I work for the Aerospace Corporation, and I'm also part of the INCOSE Automotive Working Group. Okay, I'm going to do a quick demo of a state machine diagram. So first you're going to do is right-click here. You're going to go to Create Diagram. Now we're going to scroll down to here, and now we have our initial state. And let's add 2 more states. And what I'm doing is a quick demo of a street light. So of course we make this green. Type in green. We're going to make this one yellow. Type in yellow. And we're going to make this one red. We just type in red. Now we go back here. We left click, grab the transition arrow, and grab another transition arrow. And that's a quick demo. And of course we can straighten these out a little bit. And that's it. And that's your example of a state machine diagram.
Hi there, my name is Eric Cortez. I'm a system engineer at BAE Systems, a defense contractor. My primary focus is SysML using MBSE. I've been at BAE for 5 years. I just recently received my master's degree in software architecture at Penn State University. I did my undergrad work and received an electrical engineering degree at the University of Texas, San Antonio. I've been in the defense industry for the last 16 years.
Hi, my name is Eric Cortez. I'm a system engineer for BAE Systems. I've been working primarily with MBSE SysML. I'm going to demo a state machine using enterprise architecture, or otherwise known as EA Sparks. The state machine that I'm showing is an example of a continuous integration and continuous development and continuous delivery lifecycle for software. As you notice, we have an initial node and we have a final node. In between the initial node and the final node, you have the different states. The states are code, test, integrate, release, and deploy. Now, if there's a problem with the integration of the code onto the system, we'll have feedback from that integration going back into the code and refactoring, and then go through the state again. Test, integrate, release, and deploy. Watch while the simulation is in action. Initial, code, test, integrate, but wait, are you ready to move on to the next state? let's go back and refactor the code by looking at the feedback from integration. Feedback from integration, refactor the code, test, integrate. Now, are we ready to release? Yes, we fixed the issue. Let's release. Release, deploy, final.
Integrating the power management integrated circuit and the microprocessor in an electronic control unit is an example of one of the problems of potentially having to combine components from multiple suppliers and see if they're going to work together. Here we have an example of the simulation that we've been working on in our team, in which we're showing how it might work if the power management IC was made by one supplier and the microprocessor was made by another. And we're going to run that. These have been wired together in SysML, and we're going to run this simulation to see them handshake. So here we're starting the simulator, and we see it's created instances for the power management IC and for the microprocessor, and it's gone into the factory mode where the battery has been connected at the factory. So what we do is we go to the power management IC and we feed it the ignition on signal, and here we're going to see the two components step through the initialization sequence and eventually both end up in the normal condition. Then we're going to go back and we're going to next feed it the signal that the ignition's turned off again. And likewise, we're going to see the shutdown sequence, which is non-trivial because the microprocessor has to do self-test for safety reasons. Here we see the same problem of a power management IC and a microprocessor modeled in a different tool, IBM Rhapsody. IBM Rhapsody has evolved from one of the earliest tools for simulating state machines called StateMate that was developed in the early 1990s. As we can see, the basic problem is very similar. We have the two chips wired together and each one has a state machine. However, there are some subtle differences in how the state machines work. And this is the essence of the project we're working on. In any case, we can also run the simulation in this tool. We run it here and we start the simulation, and then we can feed the events to the simulation. First, we select the power management chip and we give it the VBAT present, i.e. the batteries being connected at the factory. So the first chip comes in, and then we tell it that the ignition on signal has received, and we can see both state machines progress into the normal. And the interesting thing about this tool is it doesn't just show you the current state, but it shows you the path from the last stable state. And here we can go to the ignition off and generate it. And again, the two chips will cycle endlessly between ignition on and ignition off.
So that's it. We're a small team of working professionals and we can't take many students. However, if you're motivated and would like to work with us on this, please send me an email. My contact information is on the next screen.